Okay folks, welcome to the NUPOC video study guide number 47. We're going to skip ahead a little bit and we're going to take a look at question 1 in the differential equation section of guide 1. And calculus is the foundation of a lot of the different sections that we're going to go through with physics and electrical engineering and all that stuff. But I just wanted to take a break and start moving around the different study guides and different subjects. And so I think for the rest of this series, we're gonna move around a bit. We may go to some statics and dynamics after this, or maybe sprinkle in some electrical engineering, electromagnetics, and that sort of thing. And again, sprinkle in some of that differential and integral calculus as we go. I think it's going to be a little bit less linear from here on out, just to kind of keep it fresh. So let's take a look at this differential equation that we have here. So we're asked to solve this Diff Eq, which we can say is a second order, because it has, we go to the second derivative here of our function of x. And we have, well, I guess we could say, instead of function of x, I guess we could say x is our function, right? Or differentiating x with respect to t, so it's really a function of time. Anyways, we have a second order differential equation here, and it's a non-homogeneous differential equation. We have a forcing function out here, right? So there's some sort of input, some sort of energy being input to the system, right? This isn't equal to 0. But it's a linear differential equation, which is just to say that none of these differential terms are squared, right? As in, we don't have, let's say this is x prime, right? We don't have x prime squared times, or plus 5, or I guess this would be x double prime. We don't have x double prime squared plus 5x prime to the fourth, or something like that, right? So it's linear. So second order linear non-homogeneous differential equation. So how do we start this? Well, first, let's start by getting the general solution, which is the solution to the homogeneous version of this Diff Eq, right? So we would want to solve x double prime plus 5x prime plus 6x equals 0, right? So this is going to be, we kind of know going into this, if we've taken differential equations, our solution is going to be either an exponential form or it's going to be a sinusoidal form. So let's just choose the exponential form, right? So let's just assume here that our x of t, right, is going to equal, let's call it something like c to the c times e to the, let's just say mt, or something like that, right? Okay, so that means that our x prime is going to equal mce to the t, right? And our x double prime, right, mt, is going to equal m squared ce to the mt. So if we sub these into this, our differential equation here, right, then we get, m squared ce to the mt plus 5mce to the mt plus 6ce to the mt equals 0. Well, we can divide all the terms, including 0, by e to the mt. Those all drop out, and we're left with m squared plus 5m plus 6 equals 0. So this is just a quadratic in terms of m now. So we can just go ahead and solve this like we would solve any other quadratic, right? And we can kind of do this one sort of by inspection, right? So what are two numbers, right, that when you multiply them together will give us plus 6, right? And when you add them together, right, you get plus 5. Right? So to me, I'm thinking 2 and 3, right? So m plus 2 and m plus 3 are the two factors of this, right? So that means that the zeros of this function, right, the m's that make this equality true, these two factors equal to 0, are either m equals -2 or m equals -3. So we've got two real roots, right? And what we'll see actually is, if we get in, we're going to get into some other differential equations that represent sort of physical systems. I think in the physics section maybe, where they represent spring, mass, dashpot systems, or certainly in the electrical engineering section where it's inductor, capacitor, and resistor, or RLC circuits, right? And where the type of your roots here of your differential equation will tell you whether your system's overdamped or underdamped or critically damped. So this would be an overdamped system, right? So the response of x, right, is just going to decay with time. Of course, we are going to have this input here, so I guess I should say it's an overdamped response for the general solution to the differential equation. So we know we have these two m's, so we can say that our x, I don't know, let's call it xg for the general solution, right? Well, that's, and it's of t, that's just equal to basically c1 e to the -2t plus c2 e to the -3t, alright? But now we want to know what the solution is if we account for this this forcing function here, right? So we want to find what would be called a particular solution. So to do that, hope I have enough space left down here. I think I do. I'm just going to dash this in here. We want to assume now that our x, and I'm going to use a capital X, not to get it confused with this other solution that we have here. We want to assume cap x to be of the same form, right, as our forcing function. So if this were a sinusoid, we assume cap x to be, a cosine t plus b sine t or something like that, right? Or omega t, what have you. And if this were a constant, we would assume cap x to be a constant. So we have an exponential, so let's go ahead and assume cap x is an exponential. So I'm just going to write down here, this was the general solution. And now over here, let's do the particular. I'm running out of ink in this ink stick here, this pen. This particular solution, right? I guess it's kind of a marker, right? Sort of a Sharpie sort of thing, got a felt tip on it. It's kind of nice actually. Anyways, so we'll assume cap x of t is some constant a e to the excuse me, e to the minus t. Same form, right? So our x prime is minus a e to the minus t, and our x double prime is a e to the minus t. Right? So now when we sub this back into our original differential equation, we will get, draw an arrow over here, we will get, right, we'll get x double prime, a e to the minus t, right, plus 5, there's a negative there, a e to the minus t, right, plus 6, a e to the minus t, equals e to the minus t. So we end up with, this is a 6ae to the minus t minus 5, well that's just 1ae to the minus t, and then we add this other ae to the minus t here, right? So we get 2ae to the minus t equals e to the minus t, right? So these cancel, and we get 2a equals 1, or a equals 1/2, right? So our x of t equals 1/2 e to the minus t, right? And our final, let's see, let me take a peek here, see if you can still see that. Oh yeah, that's still on the page. Yep. Very good. So our final x of t, right, is going to equal our general solution plus our particular solution, right? And that is going to equal c1 e to the minus 2t plus c2 e to the minus 3t plus 1/2 e to the minus t. There we go. So that's the solution to the differential equation. And that does jive with the solution in the manual. So the solution manual, if you're following along. So that's good. And if we had some sort of initial conditions, or some sort of conditions where we knew what the value of x was, say at a particular time t, we could go ahead and use that, right, to solve for C1 and C2, right? And that's often what is called the I suppose the actual particular form of the overall equation. But anyways, just a nice good exercise going through and solving a second order linear non-homogeneous differential equation.